Hi there. This is Jacob Nash Algebra Lessons, and this is Unit 3, Lesson 15 on Application of Quadratics. So, you might be wondering, after 15 lessons, this seems kind of stupid. Where the heck in life would you actually use this? So, there's actually some cases where you could use this. You can use quadratics to figure out maximum heights of things, where they reach the ground, and like where it was thrown from, things like that. So, because if you know, let's just say we threw a ball, so there's a person threw a ball, it's going to go in a quadratic form. When does it reach the ground, which would be right here? The initial height, let's say that they threw it from 3 feet. So, that's how you can use it. And here's the thing that was already here. This equation is the equation that you can use to plug in things to figure out maximum heights and things like that. And actually you can't figure out the maximum height from that, but sorry, I've actually left off this part. H of t. H of t is height at time t. So that just means a certain height. That's not really the part that is important in the equation. 16, why is there 16? That number is that's there because that's taking into toll about gravity and how fast things fall. T is time, so how many seconds? In this case, you would use seconds. There's another one for other things, but v is initial velocity. So basically, hey, how fast were you throwing that? Could be feet per minute or miles per hour, depending on what it is, what equation. And h is initial height. So in this case, when there's application of anything, there's word problems. So let's go through a word problem and figure out how we would solve it. So let's do one. Okay, so a ball is thrown vertically upward with an initial velocity of 48 feet per second. So anytime there's a word problem in math, you always write down numbers because you're going to need to use them. 48 feet per second. So, okay. Hopefully, I forgot to say this. If you watch my engineering videos, I actually did the same thing when we were doing the kinematics. But anyways, so feet per second, you may have never seen that before, but that's just a unit of velocity. And it had initial height of 8 feet off the ground. This is something with part A, B, C, and D. So part A says, write a function about this, okay? What can we do? So I forgot to say that what you're finding is t, so you don't plug anything in for t. You plug in things for v, and you plug in things for h. So we keep this the same, negative 16t squared plus v. What's v going to be? We said the velocity was 48 times t plus 8 feet. That was the initial height. So there you go. B says, what is the maximum height of the ball? Okay, maximum height. Well, the maximum height always... Well, if you're throwing something up, then that means there's going to be a maximum, not a minimum. Obviously, in the real world, there's not going to be a minimum, because if you throw something down, it's not going to come back up. It's going to stay down, so that wouldn't even be a quadratic. But, anyways, that means that we need to find the vertex. The y point of the vertex will tell us what the maximum height is. How do we find the vertex? Well, this is technically in standard form, so the vertex, whenever we need to find it in standard form, is negative b divided by 2a. A, B, C. Remember, that's what it is. So, b is negative 48 divided by 2 times negative 16, which is going to be 48 divided by 32, which simplifies to 3 over 2. So that's just the x point. And we actually will need to use this later on. That means that's how long it took for it to get to its maximum height. But that's not what we were asked in this thing. So how do we find the y point? Because we just found the x point. The y point is if we plug it into the equation. Which, I mean, really the t's in this equation can just be considered x's. So, after you plug all that in, you get 44. So that means 44 feet was the highest point, the maximum. And then C says, when does this occur? We already found that out. 1.5 seconds, or 3/2 seconds, but that's usually not what you say. So, what is D? We have the last thing. State the domain and range. Okay, domain. Well, it might be a little bit simpler if we try to imagine what this would look like. So let's say we have a graph. We aren't going to do it like a cross. We're just doing it like a L because there's not negative things in the real world. Sorry. So initial height, we knew that was 8. Remember, that's what we were told. And then there's no way to graph velocity on here, so we don't need to do that. So that means this is the y-intercept. So it means it's going to start out here, but we don't know where it's going to go yet. So we found out that the vertex is 3/2, 44. So that's really 1.5. So 1.5 here. This is obviously not the scale. And then 44. So here's our maximum. And then we didn't have to find when it touched the ground, but we would assume that it would probably go something like this. So that's what our quadratic would look like. And the domain and range. Anytime in quadratics, we already learned this with the parent functions and the other unit, that the domain always has to be all real numbers. So negative infinity to positive infinity. Which, I haven't said this before, but the symbol for that is just this R that kind of looks like it has like 2 lines, like a strange R thing. And then the range is going to be, well, since it's a maximum, you know that it goes, well, I mean, technically it goes to negative infinities, but since this is a real situation, it starts at 0 pretty much, because it can't go in negative, there's not negative feet in real life. So, and then the maximum was 44, so that's how the highest point that it goes to, in brackets, because it includes those. So that is it for this video. I hope this makes sense, but that's what you'll be required to do. Oh, didn't mean to do that. And application of quadratics. Thank you for watching, and I'll see you on the next video about system of quadratic equations. And that'll be the last topic discussed, and then the last lesson is going over problems for each thing. So thanks for watching, and that'll be it.